These are the historical geology notes. And we're going to start off today. I've got both the fossil notes and the relative dating notes together. So the first section is the fossil notes, and then we'll go right into the relative dating notes. Paleontology is the study of fossils. If you think about Ross, the character on Friends, he was a paleontologist, and he always was talking about dinosaurs. Almost all fossils are found in sedimentary rocks. Thinking about the way metamorphic and igneous rocks are formed, fossils are not going to survive in anything except for the way sedimentary rocks are formed. Usually only the hard parts of organisms are saved, but occasionally whole organisms remain. Thinking about hard parts, that's bones, that sort of thing. Skin, hair, that sort of stuff decomposes pretty easily, so it doesn't get to stay around and become a fossil. And then we will talk about the different types of fossils. Preservation of organisms. Mummification is the first type of fossils. Thinking about the Egyptians, drying an organism so bacteria will not destroy it. Again, with the Egyptians, they wrap their bodies in cloth, and then they use certain chemicals to preserve the body so that bacteria doesn't eat it away and it doesn't break down. And one of the ways that you can preserve a whole organism, again, is in amber. That's the same stuff that comes out of trees. It's hardened tree sap that captures and preserves insects. If an insect lands on a tree and then sap starts coming out and encloses and encases that organism or that insect, it'll stay there in that hardened stuff. Some people actually wear things like that as jewelry, or if you think about Jurassic Park, the old man in Jurassic Park had one of these type things in his cane. Preservation of organisms still. Tar beds. That's just thick petroleum. The La Brea tar pits in California. If you guys have ever seen the movie My Girl, old movie, but they're right there in California and show the La Brea tar pits, and it's just this oil coming up out of the surface and bubbling. And then they have these large mammoths. They're kind of like elephants, statues that stick up out of it, and it's supposed to represent how they've found fossils in these tar beds in the past. And then also freezing. Low temperatures protect and preserve organisms, another movie reference. Encino Man, another older movie, but it's Brendan Fraser, and he is frozen in a solid block of ice. He's a caveman, and these people are digging up their backyard to put in a pool, and they find him in this giant block of ice, and then they follow him out, and he comes back to life, and he attends high school as a student. It's a funny movie, but that's an example of freezing. And the conditions that you need to form fossils. Sedimentary rock. Again, thinking about the heat and pressure of metamorphic rocks and the melting involved in igneous rocks, fossils just aren't going to survive in those. So it's got to be sedimentary. And of course, they have to be buried quickly so that scavengers and microorganisms don't disturb the remains. And again, it's mostly just going to be the hard body parts like bones and teeth, that sort of thing. Not any skin, nails, hair, that kind of stuff. And the different types of fossils are a mold, which is a cavity in a rock that has the shape of remains that were trapped there. Water dissolved away the remains, leaving the imprint of the original thing. A cast is a type of fossil formed when an earlier fossil in the rock is dissolved away, leaving the impression, and new sediments or mineral crystals fill the mold. So if you think about when you were little and you played with Play-Doh, sometimes Play-Doh containers would come with a shape, and you shove the Play-Doh in there and it'll make a shape. And the shape that it came with, that's the mold. And then when you put the Play-Doh in and it turns into that shape, that's the cast. So it's actually sort of the opposite of what you think of when you get your arm put in a cast. Your arm is the cast, and the mold is the shape around it. Or like a cake pan, that's the mold, and the cake itself is the cast. Carbonaceous film, a fossil impression in a rock consisting only of a thin carbon residue that forms an outline of the original organism. You see a lot of these for leaves and that sort of thing. As they fall and they get stuck in rock, the carbon in the leaf is going to decompose, but then you get the film left behind. Petrified or replaced remains. If you've ever found a piece of petrified wood, it looks exactly like a piece of wood except it's stone. Plant or animal remains that have been petrified or turned to rock. This happens when minerals carried in the groundwater replace the original remains. So the original stuff gets washed away by the water and gets filled in by minerals that harden and calcify or solidify. Think like stalactite, stalagmite, same thing. And then, of course, original remains. Original means it's not been changed at all. So these are bones and shells, teeth, those sorts of things. Trace organisms, preserved evidence of activities of living things, like footprints or tracks or trails, burrows. In the classroom here, I have a piece of sandstone, and you can see burrows from where worms have been burrowing in the sand, and then the rock, or then the sand was turned to sandstone, and I've got these pieces of sandstone where you can see evidence that those worms were there because of their burrows. Or maybe you find footprints of a certain type of animal. You know that that animal has been there. And that's where these come from. So the next set of notes, the relative dating notes. This all has to do with layers of rock. In the fossil record, fossils help to determine a rock layer's relative age, or how it's related to another layer. I always say that if I put perhaps your grandmother next to you, just by looking at the two of you, I can say, well, your grandmother is older than you because of looking at her versus the way you look. That's relative age. An index fossil is used to help determine relative age. If you find an index fossil in a certain layer, the index fossil is easily recognizable, so you know what it is. It must be found everywhere in the world, not just specific to one place. And this organism that provides the fossil must have lived for a short time period. Because if you find the organism in a layer, you want to be able to say, well, this layer must have happened between year such and such and year other such and such. Because you know that this organism that you just found in that layer only lived for that time period. So the organism must have died in that layer during the time period of which it lived. Determining the fossil record by relative age and absolute age. And we already talked about relative age as being looking at you versus looking maybe at your grandmother. Absolute age actually gives us a specific date or year. Absolute age is going to tell you the actual age. So just by putting you and your grandmother next to each other, I can't say, well, you must be 15 years old and your grandmother must be 60 years old. I can't tell that just by looking at you. I have to figure out some other way to figure out your ages, and that's absolute. Relative age is not an exact age. It's a way of telling one layer of rock is older than another, or it could be younger. Like going back to the grandmother thing. Looking at you two, I can figure out your grandmother's definitely older, but I don't know a specific age for either of you. Laws and rules govern how you determine the relative ages of rock layers and things that you find around them. And we're going to talk about all those laws and rules, and you will have to know them. The law of horizontality. Just think about the word horizon, meaning layers, like we just talked about with soils. Rock layers are laid down horizontally, never on a slant. So they're always horizontal when they get laid down. Very beginning, everything is horizontal. The law of superposition. Each sedimentary rock layer is older than the overlying younger layer. That's a little confusing. If you think about it this way, when you go to build a building, you have to build the first floor before you can build anything above it. So the older layer is going to be at the bottom, and the younger layer is going to be at the top. Here's a picture of superposition. In the Grand Canyon, you see all these different layers. The one at the bottom, that Supai group, must be old because it's at the bottom, and the youngest, the Kabob limestone at the top, must be the youngest because it's at the top. Relative age. Sometimes due to crustal movements, sedimentary layers aren't always horizontal, so they can be changed and moved around. The law of cross-cutting relationships states that at a fault or intrusion is younger than the rock layer it cuts through. So if you think about a burglar coming into your house, an intrusion is going to cut through something that's already there. A burglar can't break into a home that isn't there. So the home must be older than the intrusion. And then an igneous intrusion occurs when magma squeezes into or between layers of pre-existing rock. Again, for that intruder to break into your house has to already be there. So the rock layers must already be there for an intrusion to come through. So the intrusion's always going to be younger than where it cuts through. And then here's some pictures pointing out these different things. Here's a fault, so it's changed shape. Remember, everything starts out flat and then it can be changed. Here's an intrusion. There's that intrusion must be younger than the layers that it cuts through because it can't cut through something that's not there. Here's another intrusion, another fault. So the fault must have happened first before the intrusion cut through. Included fragments. Sometimes other things found in the rock layer give you clues about its age. Pieces of rock found in another rock must be older or formed first, because you can't have something in something if it's younger. And taking a look at your notes, if you look at the picture on your notes that is the same as this one, all we're going to do is look at it and kind of label it a little bit. We've got the law of horizontality here. All the layers are horizontal. Included fragments, these little pieces here, and an unconformity where there's been some erosion that's occurred. An unconformity is a buried surface of erosion separating two rock masses representing a gap in geologic time. And there are a bunch of different types of unconformities. An angular unconformity is flat strata deposited on top of older strata. And strata just means layers. A disconformity is missing layers due to erosion. And a nonconformity is sedimentary layers deposited on igneous or metamorphic rocks. And the principle of uniform process, formulated by James Hutton, states that the geological processes at work now were also at work in the past. So, as you may have heard before, the present is in fact the key to the past. And here on this picture, you have it as sort of a cycle written on your paper. Looking at the top left picture, the one with all the straight lines on it, that's the law of horizontality. And then you can follow how it's being changed. All these layers here are horizontality, and then an angular unconformity. This is included fragments. And then here's an intrusion. And then here's another unconformity because there's been some erosion. And again, you can just follow it around. It starts here up at the top left. Then you're adding some new layers. There's an intrusion. Then you're eroding. Then there's an unconformity. We're changing the top layers again. And then we're even adding some more again and changing it again.